Back with another exponential equation for you. We're looking at 6 to the power of x plus 3 equals 4 to the power of x. And this equation looks innocent at this point, but if you notice, remember the first thing we always try to do is we're trying to see if we can match the bases. I start with the smaller number, which is 4. And I just kind of ask myself, well, 4 to the first power is 4. 4 square is 16. So I know that I can't match it with the power of 4. So then we say, okay, what could make 4 a 2? So I know 2 to the first power is 2, and 2 square is 4. So this is great. But we want to say, can we make a 6? And you got to be really careful because we have to do this by terms of powers. So if I take 2 to the third, remember this is 2 times 2 times 2, which is 8, not 6. Be careful because there's a difference between 2 to the third versus 2 times 3. That's a really common mistake that we make when we're going a little fast. So be careful. I'll erase that so that's out of our mind. So in this case, this is not working either. So right away, I notice that I cannot match the bases. Not because I don't want to, but it's impossible with powers that we're given. So if that is the case, we have kind of a first aid to take care of this. We have new properties of logs that we've dealt with. We could actually take the log of both sides of the equation and see where that leads us. So remember, when you cannot match the bases, you can take any log that you'd like, but usually you can take the log with base 10. That's more popular because we have that already incorporated into our calculator. Or a lot of times people like to take the natural log of both sides as well. But for this purposes, I would go with the common logarithm, log with base 10. So if we do that, I'll write this in, log of 6 to the x plus 3 power equals log of 4 to the x. Now what's cool about using this property, it looks a little complicated at first, but you can use properties of logarithms to release the variables from their exponent position in the argument. So at this stage, once you take the log of both sides, we're going to use the property of, I don't know if you remember, it's log base b of x to the r. You don't have to memorize it based off of the letters, but you just kind of have to know if there is an exponent in the argument, we can take that exponent and pull it around to the front as a coefficient of the log. And that is very useful to us. So what I'm looking at, and I'll move this over here, starting to get in my way. Kind of remember whenever you take the log of both sides, these two properties go hand in hand. And at this point, I'll do that with a highlighter I wanted to show you. This x plus 3 comes around as a coefficient to the front of the log. So x plus 3 is multiplied by log of 6. And remember, if it's helpful to you, feel free. If you'd like to write the base in, you can, to remind yourself that it's base 10. I didn't, but I'll do this now. Okay, we still have the same idea. If you notice also, we have that x in the argument. That's an exponent on the 4. So along with that property, that becomes the coefficient of the logarithm. So we have 4 times log, excuse me, I meant x. Moving a little too fast here. That's why it takes some time. There we go. X times log of 4. And remember, it's still base 10. So what's really nice about this property is now your x's are out of the exponent portion. You don't really have an exponential equation at this point. In some ways, you have more of a linear sort of equation. I want you to keep in mind when you see logs that have a numerical base and a numerical argument, these are really just constants. They're decimal constants, but this kind of leads us to maybe thinking of a similar equation. So I'm going to take a sidebar, just kind of think back to maybe solving a simpler problem. Sometimes those logs look intimidating, but if you were solving an equation that the log base 10 of 6, let's say this was just a constant number, like let's say I just picked 10 because it's kind of a nice round number, and that was equal to x times another constant that's a little different. So let's just say, I don't know, totally making this up, but let's just say it's a 2 or something. I shall do that. And I'll color code so that we have this. So just kind of think about what you would do if you saw an equation like this, sans the logs. What would you have to do with the 10? He's probably answering back, oh yeah, I know I would have to distribute the 10. Well, you do the same thing with the log. So if you want to play along with me, what I'd be looking at is distributing the log of 6 to both of the terms. And so don't make it more complicated than it is. Log base 10 of 6 is just a number. So if you were distributing it to the 3, really you would probably see it rewritten as 3 times log of 6. Maybe you want to write the base in if that helps you. This is added. It's a positive 3. I should probably keep that in mind. If I multiply log base 10 of 6 to x, you would see x times log base 10 of 6. I'll try to write them kind of separate so that you see that there's 2 separate terms here. So similarly, if we were to see that happening on this side equation, what do we have? 3 times 10 is 30, 10 times x is 10x. Now, a lot of times when you saw x times 2, you probably would say, oh yeah, that's the same thing as a 2x. But usually when we see right-hand side of the equation, really there's nothing we would do here. We don't want to get the coefficient of the logarithm confused with the argument. So I'll just continue to rewrite it as x times log base 10 of 4. Now, there's a lot of logs going on, but kind of keep in mind with this simpler example we have off to the side. What would you now do if you were solving 10x plus 30 equals 2x? If you thought maybe I'll collect the variable terms on the same side, you are correct. So if you see that, you'd be subtracting maybe the 10x from both sides. And so what does that look like when we have our corresponding log equation? We're looking at the terms that have the variable x involved. We're trying to collect them on the same side. So that would involve me subtracting x log base 10 of 6 from both sides. So if we do this, you notice that they cancel out on the left side and you're left with a 3 log base 10 of 6. And when you try to simplify them on the right-hand side, they're not quite like terms due to, you guessed it, they have different arguments. So what you can do at this moment, if it helps, just write them horizontally and then we'll kind of interpret this in a second. So I have x log base 10 of 4 minus x log base 10 of 6. Now we're almost there. I just want to kind of note, if you were solving the simpler equation to give you a clue of what to do, right away you would say, oh yeah, 2x minus 10x, they're like terms, so I'm getting negative 8x. But I want you to think backwards. And back in the day, it's been a while, I know, you're automatically able to go to negative 8x, but when you used to see this, 2x minus 10x, you would use something called like reverse distribution. And you would say, oh yeah, what do I do is I can factor out the x and then just deal with the math with the coefficients. So that's x times 2 minus 10, or x times negative 8, which is negative 8x. There's a lot of steps that you took back when you were first learning, and now they're automatic. But don't lose track of what you're doing. In this case, for our actual equation at hand, we would then have to factor out or reverse distribute x from both of the terms. And if you do that, you factor out the x, you end up with log base 10 of 4 minus log base 10 of 6, still equal to 3 log base 10 of 6. So what you've just done, super powerful, you made x now a factor. And what you're really trying to do is figure out, well, if I were solving this nice equation on the right-hand side that we just made up to help ourselves, how would we isolate the x at the end? And you're saying, oh yeah, I already know that I always divide by the coefficient so that I can get that x to have a coefficient of 1 so I can solve it. Well, it's the same story here. It's just that your x has a little more complicated coefficient. But keep in mind, they're both constants. So in the end, when you subtract two constants, you'll have a constant. So how do we isolate that x? Same story. Divide both sides by that expression. Log base 10 of 4 minus log base 10 of 6. Remember, we're keeping the logs because this is a straight algebra. We're not using any log properties at this moment. So now what happens is that your x is now isolated. I'm going to have to move this over a little bit, so I will. I got a little crazy with all my side examples, but I always like to compare it to something I have a better grasp on before I jump into something else. So if you don't mind, I'm going to draw a quick arrow way out here, and I'm going to copy this over just so that we can interpret this. So I have 3 log base 10 of 6 divided by log base 10 of 4 minus, and I'm going to double check, there it is, log base 10 of 6. And that's equal to my x. Now, I've been kind of paranoid keeping the bases, but I know when it's a common log, I don't really need to have that. So I could write them even closer. We want to rewrite what I had, 6 and 4. Okay, there we go. 6, 6, and 4. So at this stage, you have solved the equation for x. And this might be the place to go if you were looking for an exact answer. So I may kind of leave this. This is really what we call the exact answer. Sometimes we prefer that so that we don't have to worry about rounding or making the problem inaccurate with the level that we take for rounding. So be careful with directions. If they ask for the exact answer, leave it as is. If they ask for an approximation, we can just pull up our TI and approximate it as well. When we're looking back at the directions, all it said was solve. So if there's no context to this equation, like we don't know a realistic situation behind it, you may just leave it in exact form. Or if they told you to round, or they gave you some specific real life situation that this involves in, you may be interested, what is 3 log 6 divided by log 4 minus log 6? So we could approximate it, and I can do that with my TI, so I'll pull that up really quick. Probably should have had this going beforehand. We'll see if it opens for us. Sometimes it takes a little while, so I'll try to entertain you with, no, I'm good. I don't have to worry about telling jokes or anything like that. Whoops, we're running out of subscriptions, so we'll try. There we go. So like I said, I'm going to move to show you just the approximation. Lucky for us, what we're looking at is we can type this in. What do we have? Log of 6. Let's double check. 3 times log of 6. There we go. Okay, so keep in mind when you're typing in fractions, you want the numerator enclosed in parentheses. And I'm using log because I use the common log. So 3 times log 6 divided by. Now the entire denominator has to be involved here. So enclose the denominator in parentheses. And we remind ourselves, what did we actually use for the denominator? So you see me clicking, you can't see me, you hear me clicking back and forth. So I should have log of 4 minus log of 6. Close the denominator. So that's the way to find the approximation. If you press enter, you now have yourself a decimal. And so that's what happens when you have these logs. You have a, what do you call it, irrational decimal that really never ends. There's no pattern. So sometimes they may ask you if you were trying to approximate. I'll write it back down for ourselves. So we should have, switch back to the screen. The approximate answer, or the approximation, would be given by x, and we'll draw the little approximation equal sign. Negative 13.25706. See if I can remember that when I write it. Negative 13.257. I think it was 06. I'm going to go back and check while you're waiting. 06775. So that's what the TI is telling you. If you wanted to take it further and round it, a lot of times they say when you don't have a rule of thumb, you just say, well, let's round it to 3 or 4 decimal places. Negative 13.2571 maybe. And sometimes that helps you really understand what the number was. So just be careful. Like I said, if the directions don't specify, it's probably safer to go with the exact answer. Or if you're using this calculation for another calculation, it's probably safer to keep the exact answer. But the approximation will also suffice if you are just trying to figure out what that actual number was. Before we move on to the next type of example, I do want to show you that it doesn't really matter what type of logarithm you take of both sides, as long as it has the same base. So I'd like to kind of show you something cool, is that one of the other ideas that we take when we're trying to take the log of both sides, sometimes people like to use the natural log, and that's fine too. I'd like to show you that we would still get the same format of the answer, but instead of having the log, you would see ln everywhere. So just kind of a side note, if you had done this, 3 ln 6 over ln 4 minus ln 6, the question would be like, are we getting the same answer? And let's test it. Let's go back to our TI. And this time, we still have to use parentheses. I have 3 natural log, that's below the log key of 6. Close that numerator. Divide by, open up, we have natural log of 4. Close the argument, subtract off. The natural log of 6. Close that argument, close the denominator, and enter. And look at that. That's really, really cool. Notice that you get the same answer no matter what log you're picking. So totally up to you. If you'd like to use natural log or log, feel free to. We only use these because they're more popular and listed on the face of the TI. If later on new technology comes about, we can use different logs with different bases, but those are the go-tos at this moment. So having said that, I might want to have a discussion about, when would it be better to use a natural log versus an log? Common log, I should say. So glad you asked. I'm going to move on to example 3 and kind of show you like, that might be kind of a situation. So right away with example 3, we're looking at, it's an exponential equation. And I know it's an exponential equation because I do see the variable in the exponent position. There's a t there instead. And you might be saying, well, wait a second. I thought e was a variable too, but not in our context. Because remember, e is Euler's number, famous mathematician. And e is approximately, it kind of works like pi. What do you have? 2.71828, 45, 90, 45, and then I don't know the rest. You ever want to know how I know this? I did not just spend time memorizing. I suppose I was told, and I need you to verify this for me. They talk about the seventh president of the United States, I guess, was elected in 1828. And maybe I am actually a bit off here. Now that I'm remembering the story, I don't know if you stuck around for this, but I actually should be rewriting this twice. And the reason why the story comes to be is that I guess the 7th president, and I should know who this is because I've been telling this story for a long time. But anyways, the 7th president was elected in 1828 and served 2 terms. And then that's how I know the 1828. And then for whatever reason, very popular mathematics triangle, 45, 90, 45 triangle. And that kind of gives you some of the letter E. Do you have to memorize it? No way. Lucky for us, when we pull back the TI, if you were interested, the E is located where the natural log key is. And if you want to access it, you just press the second natural log, and you see the E. And if you really want to know what E is, you press e to the power of 1. And then you have the approximation. So it's kind of like pi, except the 1828 does not repeat more than twice. And I guess you wouldn't know about the 45, 90, 45 triangle unless I told you about it. But feel free, look it up. And then maybe you guys can tell me who the 7th president was. I should know this by now, but I am a math teacher, so I digress. Let's get back to the subject. So E is not really a variable. In this case, it is a number. And we will notice that in no way can we match the bases. We cannot match E with 3 in terms of the bases. So right away, what is our trick? We take the log of both sides. And in this case, if you're going to try to take the log of both sides, this would be more appropriate to take the natural log of both sides. And why? Well, my friends, that E, that has to do with the natural log. And so that's us taking, ln, log natural. So showing that with you, I take the natural log of e to the 0.04t equals, I'll show you, kind of be a little more detailed there. There we go. Natural log of 3. I am running into my writing. You probably won't have all this writing for yourself. It was just me showing off, I guess. So we actually have our issue is now that you take the natural log of both sides, now we're going to use the properties of logs to remove the variable from the exponent position. So again, we're going to use, what's the property? Log base b of x to the r is the same thing as r times log base b of x. So that r is coming along to the front. In this case, we are taking this 0.04t and we're moving it along to the front. So 0.04t times natural log of e equals natural log of 3. Now, what is kind of cool and is why we would take the natural log of both sides, I'll also remind you, there is another property of logs that allows this one to somewhat disappear. And what I mean by disappear, little note, when you see natural log of e, remember that the base of the natural log is also an e. And when the bases match, what happens is the result of your logarithm or the evaluation of your logarithm is 1. So this natural log of e turns into a 1. And that's really just multiplied by 0.04t. Still equals natural log of 3. Well, what happens when you multiply anything by 1? You don't really see it anymore. You get 0.04t equals natural log of 3. And we're almost good to go. All we have to do is we're going to isolate t. We would divide both sides by 0.04. So we will get t equals natural log of 3 divided by 0.04. And again, this is the exact answer. So in this case, when we look at this, we'll say, well, there was no context to this problem. They didn't tell us to round or anything, so we can keep it and never think about it again. However, if maybe a lot of times when you're using problems that dealing with E, you're dealing with population and time, exponential decay, exponential growth, you may be interested that T is used to stand for time, and you might be caring about how many years might this be. We don't know yet because there's no context, but this would be another opportunity to see if we can approximate. So we'll just go back to our TI. And if you're going to approximate on your TI, we'd be looking at natural log of 3. And I'll be a little more precise. I think we're okay. We close the argument. We'll be divide by 0.04, I believe. I'll double check because sometimes I lose my memory there. So let me double check before I go. 0.04 it is. Okay. You can't see me double checking, but I am. And when you approximate it, you get about 27.4653. Pretty cool. So if you ever had to approximate it, the approximation t is approximately equal to 27.4653. And again, that's the approximation, just in case. Kind of depends where you take this later. So that should get you through these types of examples. I would like to point out, you know, it wasn't a requirement that you take the natural log of both sides. It just makes the problem a little cleaner, or the answer a little cleaner at the end due to that natural log of e equaling 1. If you decided to take the common log of both sides, in the end, your answer would be a little more complicated when you look at the exact version, but it would still come out to the same approximation. So just kind of go with the flow. Use what you think would be appropriate, but usually e's and natural logs go together. So hopefully by watching this example, this helps you out. Keep practicing. I'll see you in the next example.